Hello dear students, today I will discuss about Cauchy's root test. There are some more tests for testing the convergence and divergence of the series. So Cauchy's root test, okay, and then alternating series I will discuss about that. Okay, so Cauchy's root test, that is Cauchy's root test. Okay, so if it's a statement, it's very simple statement. Okay, so it can be used for determining the convergence or divergence of an infinite series, positive term series. Okay, the statement is very simple, that is in a positive term series, summation un limit n tending to infinity un power 1 by n equals to lambda, suppose. Okay, in a positive term series summation un, limit nth term, nth root, limit of nth root of nth term is equals to lambda. In a positive term series this, then if in a positive term series this limit is lambda, then this is convergent. This is convergent for lambda less than 1. Okay, and divergent for lambda greater than 1. And test fail if lambda equals to 1. So very simple statement, just nth root of nth term tending to lambda at a quantity that is less than 1, then convergent, greater than 1, then divergent. If equal 1, that this limit is equal 1, then the Cauchy's root test fail to decide whether series is convergent or divergent. Clear? So this is the statement. So very simple statement is this. Okay, so we can use this test for the testing of convergency divergency of series. Very simple, because just we know here its proof is very simple. Just because its limit is what? Limit of this is lambda. And by the definition of limit, we know by the definition of limit, similarly as a previous case for ratio test, we have already used the definition of limit. Here, if we use definition of this limit, then we can find a number. We can find R such that lambda less than R less than 1, and by using this definition of limit we can find R such that here in this case lambda less than 1, then if we can find a value R for limit by definition of limit, what? Un power 1 by n. We know just for all n is greater than equal m, or greater than m or greater than equal m, just this is less than R. Here we can get a number, because if lambda less than 1, then limit, this is less than 1, this value is less than 1. So by definition of limit, by definition of limit, okay, simple proof, it's proof, simple proof, very simple, by definition of limit, this limit. Case 1, when lambda is less than 1, first case, lambda is less than 1, then lambda, we can find R, by definition of limit we can find R, because this is equals less than R, such that, like this is less than R for all n greater than m, some numbers from starting. So here we can write un power less than R to the power n. Just apply the power of n to both sides, that we can write un is less than R to the power n for all n greater than m. Now if we omit or leave first m terms, then we can write this is un is less than R to the power n for all n. In this case, just we can see that omitting m terms, first m terms. Okay, what we get? u1 plus u2 plus up to un, or we can write like this. From here, un is less than R to the power n for all n, and from here we can find that what? Summation un is less than summation Rn, or R is less than 1, and we know that from geometric series this is convergent. Because R less than 1, this is geometric series. This is geometric series, R less than 1, that is convergent. So this is also convergent. So this is proved. Clear? R is less than 1, this is convergent. So UN is convergent, as summation Rn is convergent R less than 1. Okay, and second part, this is equal lambda, lambda is greater than 1, this limit is greater than 1. So we can find a number. So we can write because greater than 1 limit, so greater than value we can find when lambda is greater than 1. We can find a number m such that un power 1 by n, its value is greater than 1. So we can find this is greater than 1 for all n greater than m. Now neglecting m terms, we can get from here what un is greater than 1. Apply the power of n to both sides, we can get like this for all n greater than m. Omitting first m terms, we get un is greater than 1 for all n. So this imply what? un, u2 up to un, partial sum of this series, what? Greater than 1 plus 1 plus up to 1 n times. That is what? Sn is greater than n, implies Sn tending to infinitive as n tending to infinitive. So summation un is what? Divergent, because n tending to infinitive. As n tending to infinitive, Sn tending to infinitive. Sn is partial sum of this series. So for lambda greater than 1, divergent. And here test fail when lambda equals to 1. That is, its limit is 1, then test fail. And we will use further method or any of the previous method. Okay. So this is the statement of Cauchy's root test. Now take some questions from this test. Okay. Any of the basic series can be used for testing of given series for convergence or divergence. Okay. So here, the take first question, that is test the convergence of the series. Just take the question. Solution. Here given series is un equals to sum of 1 plus 1 by root n power minus 3 by 2. Okay. Minus n to the power 3 by 2. Minus n to the power 3 by 2. Minus n to the power 3 by 2. This is given question. Okay. That is here something power n. So we can use root test because power something related to n, and if we take another root, then n can be cancelled out. So that's why we can try for root test. So here un equals to 1 plus 1 upon root n power minus n to the power 3 by 2 implies un power 1 by n, because for the root test just we have to find nth root, un power 1 by n, take nth root of both sides. Okay, so here we can see that minus power, so we can write here 1 plus 1 by root n or 3 by or n to the power 3 by 2 of 1 by n. Clear? So this can be written as what? 1 upon 1 by n to the power 3 by 2 upon n means root n, or can be written 1 plus 1 by root n or root n. Okay, we can write this. Clear? Or n to the power 3 by 2. N to the power 3 by 2, this means divided by n, root n. So this tending to what? Implies the limit. Implies the limit, because here in the nth term we are having some power of as a with exponent with n. So we can use root test. Limit of this, what? Un power 1 by n. Just we are taking limit, that is a tending value. What? 1 upon limit n tending to infinity. 1 plus 1 upon root n or root n equals to what? 1 by e. 1 by e. Okay? Because we know that the limit, since limit n tending to infinity, 1 plus 1 by n or n is equals to what? E. And this is equals less than what? 1. Because e is greater than 1. So 1 by e is less than 1. Hence, by Cauchy's root test, the given series is convergent. Because if its limit is less than 1, then convergent, greater than 1, then divergent, equal 1, then fail. Here limit is less than 1, so by Cauchy's root test, series is convergent. So very simple question is this. Okay. Take a next question related to here. Second question, as a series here given 1 by 2 plus 2 by 3x. Given series is the next question, 1 by 2 plus 2 by 3 x plus 3 by 4 x square plus 3 by 4 square x square plus 4 by 5 cube x cube. This is given series. Okay, so this is the 4 by 5 cube x cube infinity x greater than 0. Here x greater than 0. This is the given series. So first of all, we have to find nth term of this series. Okay, nth term of this series. Here we see that each term having some power. So here power 3, 2, 1, and this is different type of term. Okay, So we can write its nth term. Nth term will be what? N plus 1 upon n plus 2. Because n upon n plus 1 if we take, then power, just take this, or n, and x to the power also n. Omitting first term. Okay, first term. We know that in the infinite series we can neglect first 1 2 term. Okay, so here just leave this term. Okay, so omitting first term, we can write another term like this: n equals to 1, that means 2 by 3 power 1, x power 1. n equals to 2, 3 by 4 power 2, x square. n equals to 3, 4 by 5 power 3, x3. So this is will be the nth. Okay, so here we see that power as n. So we can find its then we can find its Cauchy root test can be used because power is having with n. So n plus 1 upon n plus 2 into x. Taking nth root of both sides, we get this. Okay, so its limit is very simple finding: n tending to infinity, un power 1 by n. Here limit n tending to infinity, what? 1 plus 1 by n upon 1 plus 2 by n into x equals to what? X. Because n can be taken common, so n cancel, and 1 plus 1 by n, 1 plus 2 by n, so this is 1, 1, this is limit 1, and x. That is limit is x. Now, according to Cauchy's root test, if this is less than or convergent, greater than divergent, equal. So, by Cauchy's root test, is convergent for x less than 1, divergent for x greater than 1, and test fail for x equals to 1. Now for this x equals to 1, we have to check by any other test, using any other test. Okay, so here for x equals to 1, we have un. What is un? Un is this. For x equals to 1, here x equals to 1, so its value will be what? N plus 1 upon n plus 2 power n. For x equals to 1, this. Now from this we can see that the limit of this can be find what? N plus 1, here n plus 2. So just do like this. N plus 1 upon n plus 1 common n plus 2. That means you can write n plus 1 plus 1 whole power n. This is equals to what? Just taking n plus 1 common, n plus 1 cancel. So 1 plus 1 by n plus 1. So 1 upon 1 plus 1 upon n plus 1 power n. That is what? 1 upon 1 plus 1 by n plus 1 power n. Okay. This type we can write because n is the power. So here n plus 1, n plus 1, n plus 1 can be taken common. So n plus 1 cancel. So 1 upon 1 plus 1 by n plus 1. So it can be written like this. Now n tending to infinity, this is tending to infinity, this is tending to 0. So this is e, 1 by e, tending will. So implies limit n tending to infinity un equals to 1 upon e. Limit n tending to infinity un equals to 1 by e, because un equals to this, and this here n tending to infinity means this n tending to infinity, this total tending to 0. So we know formula, what formula? 1 plus 1 by n power n tending to e. So this is formula. So that is n tending to infinity, this is 0. N tending to infinity, this is tending to 0. So equals to e. So 1 by e, tending value 1 by e. This is not equals to 0. So un not tending to 0. That is why Cauchy's fundamental test for divergence series is divergent. We know un not tending to 0, that means for a series un not tending to 0, that means by Cauchy's fundamental test for divergence, summation un is divergent. Clear? Cauchy's fundamental test for divergence, summation un is divergence. That is for x equal to 1, divergent. So for x greater than divergent, equal also divergent. So x, finally we can say the series is diverges for x greater than equal 1. So finally we can write what? Finally we get given series is convergent for x is less than 1 and divergent for x is greater than equal 1 for both, for equal and also greater than, divergent. Okay. So this is very simple technique for testing series, whether it is convergent or divergent, by using Cauchy's root test. Cauchy's root test is simple. Just take nth root of the nth term and find its limit. If less than 1 convergent, greater than 1 divergent, and equal 1, test fail. Okay. Now question, take another questions for so take another question. This. Okay. Here nth term is just given. Here nth term is given. What? N plus 1 power n. Here nth term is given. What? N plus 1 this is the given. In this series it is given that nth term is this. N plus 1 power n, n plus 1 power n, n power n plus 1 x to the power n, and from 1 to infinity. This is an nth term. So here also we see that power n, power n, power n. So we can take nth root of this. Clear? U1 equals to this. So we can write it how? Just we will take nth root. So here n plus 1 or n power n. So we can write like this into 1 by n into x to the power n. Because n power 1 is this, n power n is this, and n plus 1 power n is this. Implies un power 1 by n. Just take nth root. Then we can get like this. N plus 1 upon n. Nth root will be taking nth root on both sides. So here n into 1 by n 1 and 1 upon n to the power 1 by n into x. Now taking limit n tending to infinity un power 1 by n, just take its limit. So limit n tending to infinity of this means what? 1 plus 1 by n. Limit of this we can write also like this, 1 upon limit n tending to infinity n power 1 by n into x. X is free from n, so we can write like this. This is equal, this is 1. This is 1. X, limit is x. Since limit n tending to infinity n to the power 1 by n equals to 1. Okay. This is a standard result. So we can find limit very easily. So it's 1, final limit is 1. Therefore, by Cauchy's root test, is right here. x. Therefore, by Cauchy's root test, series is convergent for x less than 1, because limit is what? 1, as similar to the previous question. This is convergent for x less than 1, the divergent for x greater than 1, and test fail for x equals to 1. Now we will test what? For x equal to 1. This. Okay. So here, for x equals to 1, for x equals to 1, we get un. What will be the value of un? Un equals to x equals to 1. X equals to 1, here 1. So, n plus 1 or n upon n plus n power n plus 1. So, this can be written what? N plus 1 upon n power n into 1 by n. This. Okay, that is what? Un equals to, because another technique we will try for getting convergence or divergence of the series. So un equals to here 1 by n, just 1 plus 1 by n or n. So from here, from this un we can find Vn for the comparison test. Okay. So if we take Vn equals to let Vn equals to 1 by n, then Vn equals to sum of 1 upon n is divergent, as 1 upon n to the power p is divergent for p is less than equal 1. Clear? P is less than equal to 1. So Vn is divergent. Let Vn equals to 1 by n. Then summation Vn equals to, this is divergent as summation 1 upon n to the power pp series is divergent for p is less than equal 1. Here equal 1, p equal 1. Okay? Let Vn. Also, we see that un upon Vn limit n tending to infinity for comparison test. This is the condition for comparison test. So limit n tending to infinity, limit n tending to infinity, this limit n tending to infinity un by Vn, un upon Vn, that is 1 by n will be cancelled. Now will power n, this is equals to e, is not equals to 0 and finite. Okay, which is finite and non-zero, that is not equals to 0 and finite. So we can write also like this, which is finite and non-zero. So by comparison test, summation un and summation vn converges or diverges together as summation vn is divergent. Summation vn is divergent. The series un is also divergent. So finally we can declare given series is convergent for x is less than 1, just converges for x is less than 1, and divergent for both. For both means x greater than and 1. Okay, so this is divergent if x is greater than equal to 1. Okay, so this is a simple test, that is Cauchy's root test for testing convergence and divergence of the given series. Okay, so next our topic and also some of the other methods to finding convergence or divergence of a given series is also available there. So here alternating series, conditionally convergent series, absolutely convergent series. So just we have to know what is alternating series. Okay, so alternating series, alternate means on after on, just we are getting negative sign, that is plus sign then minus sign, plus sign then minus sign, plus minus and so on, or minus plus and so on. So this type of sign is if are there in the given series, and terms are numerically less than its preceding terms. So sir, first of all, alternating series. Alternating series. What is alternating series? Alternating series is this. Suppose a term of series u1, u2, u3 and u4 and so on up to un and so on, infinite series. So alternating series is what? If the terms of the series are alternately positive and negative. Okay, terms are alternately positive and negative, then we say this series is alternating series, just like u1 plus minus and then what? Plus and so on. So un plus minus 1 to the power n plus alternating series. What is alternating series? Just terms are alternative positive and negative. Okay. A series in which terms are alternately positive and or negative called alternating series. This. There is Leibniz test. Leibniz test for convergence of alternating series. Leibniz test. Leibniz test for convergence of alternating series. Alternating series means we know that alternately sign will be positive and negative. That is alternate series. Now, for this alternating series, how can we determine whether this alternating series is convergent or divergent? Leibniz test is available. Okay? So, according to this Leibniz test, an alternating series. We know alternating series means what? Terms are positive and or negative. So we can write like this and even. Because n equals to 1, then negative, n equals to 2, then positive, negative, positive, negative, alternating series. Okay? So alternating series, also you can write an alternating series u1 minus u2 plus u3 minus u4 infinite series. Alternating series is convergent if first and second there are two conditions: divergent if so alternating series is convergent. First condition, each term numerically less than its preceding term. Second, limit n tending to infinity un equals to 0. This. Clear? Divergent if limit n tending to infinity un is not equals to 0. Oscillating. Oscillating. Leibniz test for convergence. If alternating series is this and each term is numerically means taking positive sign, modulus of all each term. So each term numerically less than its preceding term, just decreasing numerically, and limit un equals to un tending to 0. Then we can say series is convergent. If un does not tending to 0, not limit is not equals to 0, this un does not tending to 0, then series will oscillate. If this, in addition, each term is numerically less than both. Okay. So this is for convergence, this is for oscillator. So this is Leibniz test, numerically less than preceding term and tending to 0. convergent. If not tending to 0, divergent. Clear? Yeah, sorry, not divergence, oscillatory. Okay? So this is Leibniz test. For this Leibniz test, see example. For example, like this. For example, 1 by root 2, 1 by root 3, 1 by root 4, plus minus, plus 1 by root 5, minus, and so on. This is given series. Okay. 1 by root 2, 1 by root 3, 1 by root 1, 1 by root 2, 1 by root 3, 1 by root 4, 1 by root 5, and so on. This is an alternating series. For example, this is alternating series. This is alternating series because positive terms are alternately positive or negative. Clear? And here we see that here we see that nth term. What is nth term? Modulus of nth term is 1 upon root of n. Modulus of nth term 1 upon root n. Clear? And difference mod un minus mod un minus 1 is equals to 1 upon root n minus 1 upon root n minus 1. Here see, it is preceding term. Its value is less value. Its value is greater value. So this is negative. This is negative. This is less than 0. 1 by root n is, this is root n is greater than root n minus 1. So 1 by this is less than 1 by root n minus 1. So this minus this is less than 0. That is mod un is less than mod un minus 1. Un means for the un minus 1 is preceding term and following terms is un. So here we see that un is less than un minus 1. That is, term is less than its preceding term numerically. Okay. So here for this we can write un is less than mod un minus 1. First condition satisfied. Now second condition, limit n tending to infinity 1 upon root n is equals to 0. Because nth term is this mod nth term. So un tending to 0. So tending to 0 and this first both conditions satisfied. So both conditions satisfied. Both condition satisfied. By using this technique, just modulus value, just taking positive value. So this type of relation we can get. That is, here terms is less than numerically its preceding term. That is this first term, first condition satisfied. And second condition, its limit 0 and integration 1 upon root n 0. So both condition satisfied. Therefore, this series is convergent by Leibniz test. Leibniz test. This Leibniz test says what? For a series, if term numerically is less than its preceding term and un tending to 0, these two conditions satisfied, that is, series is convergent by using Leibniz test. Okay, so this is an example for alternating series to be convergent due to Leibniz test. Okay, so by Leibniz test we can also determine the convergence of the series. We can identify whether the given series is convergent or not if series is alternating series. Alternating series means what? Alternately terms are positive or negative. Okay, so this is if un does not tending to 0 and terms are numerically less than its preceding term but limit does not tending to 0, then series will be oscillatory. Okay, so this is due to Leibniz test and alternating series. So there are some terms also related to convergence, divergence as a absolutely convergent, conditionally convergent. So here alternating series and further alternating series can be categorized two types of convergent series, just like there are two types of alternating series. Two types of alternating series. First is absolutely convergent series. Second is conditionally convergent series. Okay, conditionally convergent series. Means alternate series are there. Is terms are alternately positive or negative, called alternate series. Okay, an alternative series can be categorized like this too, because there are alternately signs changes, positive, negative. So here absolutely convergent series means what? If u1 minus u2 plus u3 minus u4 and so on be such that means this is alternating series. If this be such that its absolute value, the term absolute value of its term, that is series of absolute value of its terms is convergent. Then summation un is called convergence series. Clear? If series is absolutely convergent series. That means if this is an alternate series, it can be also written like this: minus 1 to the power n minus 1 un. Just put n equals to 1, then the u1, n equals to 2, then minus u2, n equals to 3, then plus u3, n equals to 4, then minus u4, and so on. This is alternating series. If in this alternating series be such that it's taking its modulus value, absolute value, the series of absolute value of terms is convergent. If this series be such that this is convergent, then called absolutely convergent series. Absolutely convergent series. Okay? And second, what? Conditionally convergent. Conditionally convergent series. Convergent series. If summation minus 1 to the power n minus 1 un is just you have to write here un. Okay, un. Because sign is with this term. Now, and also you can write simple this. Then the series is called absolutely convergent. If series u1 minus u2 minus u3 plus minus is convergent, but is not convergent. Then series is called conditional convergent. So clear, it is very clear that if for a alternating series, if series this is convergent, that is alternating series. If this alternating series is convergent, but its series of absolute value of its terms is not convergent, then this series is conditionally convergent. Means itself series is convergent, but absolute series is not convergent. Absolute series means absolute series of absolute value of its terms is not convergent. Then that is conditionally convergent. Conditionally convergent. And here absolutely convergent means if series be such that series of absolute value of its term is convergent, then the series is called absolutely convergent. So absolutely convergent means what? Like this. Here is such that this summation un is such that summation modulus of un is convergent. Absolutely. Absolutely. Clear? And here summation un is convergent, but summation mod un is not clear. Summation un is convergent, but summation mod un is not convergent for alternating series. These are the alternating series. Alternating series. Alternating. Alternating series. This is alternating series. Alternating series. Whenever alternating series is such that its absolute series of absolute value is convergent, absolutely convergent. This series be such that series of absolute value is convergent, absolutely convergent. Alternating series. The alternating series is convergent, but its absolute series is not convergent. Conditional. Clear? Okay, so this is conditional convergence series and absolutely convergent series. Here one result is very, very important. If a series is conditional, absolutely convergent, then it is series itself is convergent. Okay. So just here an absolutely convergent series, absolutely convergent series. That absolutely convergent series means regarding alternating series. So absolutely convergent series necessarily is necessarily convergent, but converse is not true. An important result. Okay, so note down. Note. An absolutely convergent series. Absolutely convergent series is necessarily convergent, but converse is not true. That means if a series is absolutely convergent series, so let this is absolutely convergent. Means if a series is absolutely convergent, then it is necessarily convergent. Means if we suppose this is absolutely convergent, then we can show that it is convergent. Then absolutely convergent means according to definition of absolutely convergent series. According to the definition of absolutely convergent series, this series is convergent. If this is absolutely convergent, then this is convergent. and we see that what u1 plus u2 plus and so on is less than equal u1 plus u2 plus and so on. Okay, just like this. Since u1 is less than equal mod u1, u2 is less than equal mod u2, because modulus value u1 is less than equal mod u1, u2 is less than equal mod u2. So we can add this. So u1 plus u2 plus u3 plus infinity is less than equal mod u1 mod u1 mod u2, and this is which is convergent. Convergent. This is convergent because this is absolutely convergent. So this is convergent. So this is convergent. Convergent. This series is less than. Implies summation un is less than equal convergent series. Implies summation un is also convergent. Convergent. Okay. So absolutely convergent, the series is convergent. So absolutely convergent series is necessarily convergent, but its convergence is not true. Okay, you can prove it by taking example. Okay, by taking example. Just we will solve some questions. In that questions you can see that converge is not true. So these are the discussion about conditional convergence series and absolutely convergent series. And every absolutely convergent series is also convergent, but converge is not true. So remember this for determining the convergence and divergence of series at the time of, okay, because alternating series, they are the alternating series. So take one of the questions regarding, just take some example about this. So here take the question. Given series is 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, minus, plus, minus, plus, minus, and so on to infinity. This is a given series. Okay? This is convergent but not absolutely convergent. Okay. Here given series is alternating series. Given series is what? Alternating series. And also here we see that and mod un plus 1. Modulus means absolute value. Okay, so mod un and mod un plus 1. This higher value is less than, because terms numerically less than means modulus value. Here see mod of un is what? 1 by n. Mod of un plus 1, what? 1 by n plus 1. Taking negative, positive sign. So, since n is less than n plus 1, implies 1 by n is greater than 1 by n plus 1. So, mod un is greater than mod un plus 1. And this first condition. Second, this is what? Each term is numerically less than its preceding term. Okay. And second, what? For alternating series, for Leibniz test, limit n tending to infinity mod un. You can take mod un. What? Limit n tending to infinity 1 by n equals to 0. Clear? Limit n tending to infinity. This. So, both conditions of Leibniz test are satisfied. Therefore, given series is convergent. Given series is convergent. Okay? And but not absolutely convergent this series, but not absolutely convergent. So absolute series of absolute values. So we can write series of also series of absolute values of terms of given series is what? 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus and so on is equals to 1 upon n to the power p, where p is equals to 1. Also, series of absolute values of terms of given series is this. This is summation 1 by n to the power p, p equals to 1, which is divergent as p is less than equal to 1 in p series test. Less than equal 1, then divergent. So absolute series implies is not convergent. Absolute value is not convergent. This is not convergent. Implies series is not absolutely convergent. Absolutely convergent. Series is not absolutely convergent. Because this is not convergent, this is divergent, not absolutely convergent. Series is convergent, but its absolute series is not convergent. That is not absolutely convergent series, but not absolutely convergent series. Okay. take another question, that is what? Series 1 minus so given series is this 1 minus half 1 by 2 square plus 1 by 3 square minus 1 by 4 square there na plus infinity. So here what can we say about this series? So it is an alternate series, alternating series such that it is an alternating series such that first condition mod un equals to what? 1 by n square and mod un plus 1 equals to 1 by n plus 1 square. Okay, and the square. So here we can see that n is n square and n plus 1 square. Un plus 1, mod un plus 1 is less than mod un. First condition. Second condition is what? Limit un tending to 0 or not. Limit n tending to infinity mod un equals to limit n tending to infinity 1 by n square is equals to 0. So by Leibniz test, the given series is convergent. Given series is convergent. Clear? Secondly, now absolute value series is 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square plus and so on to infinity equals to what? 1 upon n to the power 2. 1 upon n to the power 2. That is 1 upon n to the power p, where p is greater than 1, implies which is convergent by P series test. Clear? Convergence series. That is, this is convergent. Implies given series is absolutely convergent. Absolutely convergent, because this is convergent, absolutely convergent. Absolutely convergent, then series is necessarily convergent. So here the given series is absolutely convergent. Okay. So these are the discussion about absolutely convergent series and conditional convergent series. And whenever a series is convergent, then here we see, you can say that this is an alternating series, this is absolutely convergent series. So here also we see that this is convergent series. So absolutely convergent series is convergent. But in the previous questions, conditional convergent series. The series is convergent but not absolute value series is convergent. So that is the conditional convergent series. Not absolutely that. Here absolutely convergent. Okay, so these are two questions for discussion about conditional convergent series and absolutely convergent series. Okay. Take next question. Discuss the convergence of the series minus 1 to the power n equal to 1 to infinity. The series is given as given series is sum of n equals to 1 to infinity, n equals to 1 to infinity minus 1 to the power n, n upon n square plus 1. So this is given series. Okay. So n upon n square plus 1 minus 1 to the power n equal to 1 to infinity. This is a given series. Just we have to determining whether it is convergent or divergent. Here only n is involved here. So minus 1 to the power n is in this, another term is there. That means we can say that it is an alternating series, because if we put n equal to 1, then minus sign, and then n equal to 2 plus sign, minus plus minus plus minus plus. That is, it is an alternating series, as its terms are alternately positive and negative. Clear? Alternately positive and negative. So it is an alternating series. An alternating series, by Leibniz test, we can determine its convergency or divergency. Convergency, as if each term numerically less than its preceding term and you are tending to 0. So here just see numerically, that means here un modulus numerical value. So numerical value means minus 1 to the power n will vanish as plus sign. So n upon n square plus 1, and un plus 1, just one step ahead term is what? This is equals to n plus 1 taking modulus sign. Okay, so this is upon n plus 1 square plus 1. In place of n, just we can write n plus 1, this, also un minus un plus 1. So negative means u1, u2 up to un plus 1. This term is numerically less than this term means this minus this is greater than 0. So it should be greater than 0 if we solve. Also, here this we see that sign. If this is greater than 0, then alternately then numerically less than will be. So here n upon n square plus 1 minus n plus 1 upon n plus 1 square plus 1. It can be solved by taking LCM. Okay, so this LCM means n square plus 1 into n plus 1 square plus 1 and n square plus n minus 1. We can write it just like taking LCM, this into this minus this into this, and after solving we can get like this value. Okay, so this is after solving this LCM, taking LCM and just reducing, we can get like this. And here this is positive, n start from 1, so this is always positive. 1, 1, only subtract 1, so this is positive also, so this is greater than 0 for all n equals to 1, 2, 3 and so on. Okay, implies mod of un is greater than mod of un plus 1. Implies each term is numerically less than its preceding term. This is first condition of Leibniz rule. Okay. Also, limit n tending to infinity, limit n tending to infinity, n upon n square plus 1, limit n tending to infinity, 1 upon n plus 1 by n equals to 0. Equals to 0. Okay. So this is equals to 0 limit. That is both conditions are satisfied. Un, you can also write mod un or this tending to 0 or only un, that means with sign. Okay, but for testing we can take it mod un. So here, so both condition of Leibniz test are satisfied. Okay. Therefore, given series is convergent series. Convergent series. Convergent. This is convergent series. Alternating series and both conditions are satisfied of Leibniz test. So given series is convergent series. Okay. Take next question. Test for convergence and also absolutely convergence. Here one thing is very, very important for understanding, that since an absolute convergent series is convergent, so for testing the given series is convergent or not, we can test for absolute convergence. If absolute convergent, then series will be convergent. Okay. Absolute convergence means what? For the series, if this is convergent, then this is absolute convergent. Absolutely convergent. Since every absolutely convergent series is necessarily convergent. That is, if this is convergent, then this convergent. Alternating series. If this is convergent, alternating series. For an alternating series, that is for alternating series. For alternating series, if is convergent, then is also convergent. We know. So for testing of convergence of the series, we can test for absolute convergence. For testing of this, whether this is convergent or not. If this is convergent, then alternative series is convergent. Because absolutely convergent series is necessarily convergent. So in the case of alternating series, we test for this, whether this is convergent or not. And when we take modulus sign, that means positive value. That is this series of positive terms. So for the series of positive terms, we can use any of the tests before we have already discussed, just like comparison test, ratio test, etc. Okay. So for an alternating series, for testing convergency of the series, just we have to test for convergency of this, that is for absolutely convergent series. Okay, and we can use ratio test, etc. because all the tests can be applied to here because this is series of positive terms. Okay, so here if this is positive terms, so for an alternating series, we can define ratio test as what? Un plus 1 upon un modulus tending to less than 0, less than 1 and greater than 1 and equal 1. Redefine ratio test for this, because this is modulus sign, this positive term series. So in place of un plus 1 and un, just we can take modulus. So this can be also tested. So ratio test can apply by finding value un upon un plus 1, tending value is greater than 1, convergent, less than divergent, less than 1. So ratio test can be used. In place of un upon un plus 1, we just take modulus of un upon un plus 1 for the convergency of this series. If this is convergent, this is absolutely convergent, and the series is alternative series will be convergent. Clear? Main thing. So here, test the convergences of the and absolutely convergence of the series, given series. So take next question, that is here what is given? The given series is minus 1 to the power n minus 1, we can write, because if we take in place of minus 1 to the power n minus 1, then we can get sign from plus minus from start from plus sign. Okay, so minus 1 to the power n minus 1, that means first sign will be plus, then minus, and so on. So here in the given questions, here un equals to minus n minus 1 in the given series. Minus 1 to the power n minus 1, here we can take un minus 1 to the power n minus 1, 1 upon n root n. 1 upon n root n. Series un equals to this. Given series is what? 1 minus 1 upon 2 root 2. Here not x, plus 1 upon 3 root 3 minus 1 upon 4 root 4. This is given series. Okay, this is the given series. So we can write, because minus 1 to the power minus 1, n equals to 1. If we take n equals to 1. So here if we take n equals to 1, it can be written is how? N equals to 1 to infinity minus 1 to the power n minus 1, 1 upon n root n. Clear? So un can be taken like this. This is the series. Summation un. Where un equals to n minus 1, 1 upon n root n. Okay. So it can be written as what? Un equals to minus 1 to the power n minus 1 minus 1 upon n to the power 3 by 2, because n to the power 1 and n to the power 1 by 2, 3 by 2. So this is the series. Okay, so here we see that the given series is an alternating series. Okay, so it can be written also, given series can be written also, in which terms? Because you can ignore it for testing condition of Leibniz test. We can write sum of un n equals to 1 to infinity. Un means this. So sum of n equals to 1 to infinity minus 1 to the power n minus 1 into 1 upon n to the power 3 by 2. So this is equals to n equals to 1 to infinity minus 1 to the power, suppose this is a, where an equals to 1 upon n to the power 3 by 2. For using Leibniz test, just we can consider only of this part. This gives the sign plus minus plus minus minus plus minus plus. So except this can be written as a an. And for this an, because if we take modulus of this, we will get what? N. So for this n, we can test decreasing, numerically decreasing, then its preceding term and tending to 0. Here or now, we can write like this. Now we see that an plus 1 equals to what? N plus 1 power 3 by 2. And An equals to 1 upon n to the power 3 by 2. Implies An minus An plus 1 minus An equals to 1 upon n plus 1 power 3 by 2 minus 1 upon n to the power 3 by 2. Okay, so this is negative. Since n power 3 by 2 n plus 1 power 3 by 2 is greater than n power 3 by 2, implies 1 by n power 3 by 2 less than n 1 upon n power 3 by 2, implies 1 upon n plus 1 power 3 by 2 minus 1 upon n power 3 by 2 is less than 0. Because n plus 1 power 3 by 2 and n power 3 by 2. So n plus 1 power 3 by 2 is greater than n power 3 by 2. So 1 upon this is less than 3 by 2. So this minus this is less than 0. So this is less than 0. Implies An plus 1 is less than An. That is, term is less than, numerically is less than its preceding term, which is first condition of Leibniz test satisfied. And second is what? Second tending to 0. And An equals to 1 upon n to the power 3 by 2 tending to 0. That is, as n tending to infinity. That is, limit n tending to infinity, n equals to 0, which is second condition of Leibniz test. Okay, so both conditions satisfied. So both condition are satisfied. Therefore, given series is convergent. Okay. So by Leibniz test, first condition satisfied, second condition satisfied. So we can write by Leibniz test, the given series is convergent. Given series is convergent. Okay. So we are test that this is convergent series, and also we have to check it for absolute, whether it is absolutely convergent or not, whether this series is absolutely convergent or not. We see that mod of un is equals to what? Minus 1 to the power n minus 1, 1 upon n to the power 3 by 2 is equals to what? 1 upon n to the power 3 by 2. This is tending to 0. And also mod un equals to this. So by P series test. So by P series test, because for absolutely convergent series, just we have to prove that. So we get sum of series of absolute values is equals to sum of 1 upon n to the power 3 by 2. That is 1 upon n to the power p. P is equals to 3 by 2 greater than 1. Implies is convergent by P series test. Modulus. This will be plus sign, so 1 upon n to the power 3 by 2. 3 by 2 is greater than 1. So by P series test, series of absolute values is convergent. That is absolutely convergent. Hence, series is absolutely convergent. Series is absolutely convergent. Okay. This is convergent, so series is absolutely convergent. Series itself is convergent also. Series also absolutely convergent. Okay. Now question. By using this technique of alternating series, if the given series is alternating, that is alternately sign positive and negative in a series, then we can try for testing convergence and divergence by using Leibniz test, and also by testing whether this is absolutely convergent or not. If absolutely convergent, then we can also say that the series is convergent, because every absolutely convergent series is convergent. Okay. Now we are having some special type of series for testing of convergence, the C power series. We know power series, so convergence of power series. Convergence of power series. So very simple for discussion. We know power series means what? Power series means a variable having powers in increasing order. Just like this. Suppose power series what? Sum of un. Here only for discussion. Power series, exponential series, binomial series, logarithmic series. What is the interval of convergence? So here, just first of all, we are try to understand what is the interval of convergence of the series of power series. Suppose we are having a series just like this. X power series is x to the power 0, x to the power 1, x to the power 2, x to the power 3, and so on. A variable having powers 0, 1, 2, 3, 4, 5, 6, 7, and having constant a 0, a1, a2, a3, and so on, and plus it. So we can write plus a x to the power n. So this is the power series. Here x to the power 0 means what? 1. So we can write a 0 only. X to the power 0 means 1. So this is power series. If we are using this notation, then here un equals to what? An x to the power n. Here an are independent, where ans are independent of x. This is power series, known as power series. So for testing of convergence of this series, just we have already done many of the questions involving power in x. Okay, so for testing of this series, also we can use that method, just ratio test. Okay, for using ratio test, because for testing of a series, now we will use ratio test as in place of un upon un plus 1, we will take this. If this is greater than 1, limit convergent, less than 1, divergent, equal 1, fail. Means our ratio test will be like this. Ratio test. We take modulus value, because if modulus value, then will be absolutely convergent and series will also convergent. So we can use modulus sign for that. Okay. So for this power series, for testing, for which value of x the series is convergent, just we have to find. So here we have what? Un upon un un plus 1 upon un, just as ratio test, this is equals to what? Un plus 1 means n plus 1 x to the power n plus 1 upon an x to the power n. This is equals to what? An plus 1 upon an into x to the power 1. This. Okay? Implies limit n tending to infinity, un plus 1 upon un equals to limit n tending to infinity an plus 1 upon an into x equals to kx, where limit n tending to infinity n plus 1 upon an equals to k. Suppose its limit is k, then kx. Clear? Now, this series will converge if this limit by ratio test, the power series will be convergent if modulus of kx is less than 1. Will be convergent if this, or we can write here, will be convergent if mod kx is less than 1 by ratio test, because its limit is this. Here why we are taking modulus sign? Because if we take here modulus sign, then for positive term series, that is series of absolute value will be absolutely convergent and series will also convergent, because an absolute convergent series is necessarily convergent. So we can take its modulus sign. Okay. So if we take its modulus sign, that means we can take modulus is less than 1, convergent. This power series will be convergent if this. If modulus this, then absolutely convergent, then series will convergent. So this means what? Minus 1 is less than kx is less than 1. That is minus 1 by k is less than x is less than 1 by k. That is x belongs to minus 1 upon k and 1 by k. That is for value of x lying in this interval. That is x belongs to this. This is the interval. In this interval, series is convergent. That is, in this interval, series is convergent. It is called interval convergent. It is called interval of convergence. Interval of convergence. This interval is called interval. Well, k is what? Limit of this. So, interval of convergence. Okay, for the power series. So, minus 1 by k to k for convergence. In this interval, series will convergence. Outside this interval, series will be divergent. Okay. So, power series, for the convergence of the power series, for which value of x the series is convergent? For this value of x, that is interval of convergence of the power series. Interval of convergence of the power series is minus 1 by k, 1 by k. Where k is what? Limit of this. N plus 1 upon n. Limit of this is equals to k. Okay. So, remember it for solving. Actually, all the series we have already tested for convergence and divergence, which involving x as a power, this power series for testing, but we can find the value of x for which series is convergent, or for another value for which series is divergent. Okay. So this is the convergency of power series. That is interval convergence of power series. Okay. So take some questions related to this. So find the value of x for which the series is convergent, the given series. Okay. X 1, 2, 3, 4, 2 square, 3 square, 4 square. So here question is given. So power series can be tested by using which method? By this method. You can find interval of convergence for the given series. So take question. In this question, the given series is what? X minus, because x to the power 1, 2 and so on. Here series is x minus x square by 2 square plus x cube by 3 square minus x power 4 by 4 square. This is series. Okay. Here un equals to nth term can be written as what? Nth term can be written as first plus sign, then minus, plus sign, then minus, alternating series. So what? Minus 1 to the power n minus 1, n equal to 1, then first time positive and then negative, positive, negative, positive, and so on. Here x to the power n upon n power 2, x to the power n by n square. Okay, now this is an power series because x to the power n power in x, so it can be checked for convergence by using ratio test. Okay, for ratio test, we will find the value of minus 1 to the power n plus 1 minus 1 and x to the power n plus 1 upon n plus 1 square. Okay, therefore un upon, just we are finding this value. So remember the ratio, in which type you are finding ratio. This is equals to what? Un plus 1, this minus 1 power n plus 1 minus 1 x to the power n plus 1 upon n plus 1 square into divide by un. So minus 1 to the power n minus 1 into x to the power n square. So it can be adjusted a square square. So n upon n plus 1 square minus 1 to the power n minus 1 minus 1 to the power n minus 1 cancel. So 1 minus is there. So minus 1 and x. Okay, so just see limit n tending to infinity un plus 1 upon un equals to minus x, because its limit is what? 1, n cancel, 1 upon 1 plus 0 square, so 1, this is minus 1 minus x, it is minus x. So by de-elaborate test, it is alternating series. By de-elaborate ratio test, this is equal to this. Modulus we can take. So here we can write its modulus value. So by de-elaborate ratio test, the given series is convergent if mod x is less than 1. Here for alternating series we will use modulus value. So we can take modulus sign. So modulus of this means what? Modulus of minus x equal to mod x. So mod x is less than 1. Un plus 1 upon un. So mod x is less than 1 for this convergent. That is minus 1 less than x less than 1. Okay, convergent. Here for x equal to 1 and x equal to minus 1, we have to test further. For x equals to 1, we see that for x equals to 1. For x equals to 1. For x equals to 1, the series for x equals to 1, sum of un is equals to what? X equals to 1. 1, 1, 1, 1. So 1 minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square plus and so on to infinity. This is series. And this is what? Alternating series for x equal to 1. This is alternating series and each term numerically less than the previous term. And also 1 upon n square tending to 0. So by Leibniz test, for x equal to 1 this, which is an alternating convergent series. Convergent series, alternating convergent series by Leibniz test. Alternating convergent series, very clear. Each term is numerically less than the previous terms and un tending to 0 here. So this is by Leibniz test, convergent series. So x equal to 1, convergent. And for minus, x equal to minus n also. Also for x equals to minus 1, we see that x equal to minus 1, we see that series is what? Or minus 1. This is minus 1. This is minus 1 by 2 square. This is minus 1 by 3 square. This is minus 1 by 4 square. That is minus 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square plus up to infinity. That is what? Minus sum of 1 upon n to the power 2. Clear? Which is also convergent for by E series test as P equals to 2 is greater than 1. Convergent. That is, this is convergent. So also for minus 1 convergent. For 1 convergent, for minus 1 convergent, and in this interval convergent. Therefore, we can write the interval of convergence is what? Including minus 1 and plus 1. So we can write hence the interval of convergence is minus 1 is less than equal x is less than equal 1. That is for the values of x which lies between minus 1 and plus 1, and also at x equal to 1 and x equal to minus 1. This is the interval of convergence, is this. Okay. So this is the technique for finding the values of x for which the given alternating series is convergent, a power series is convergent or not. For testing whether power series is convergent or not, that is for finding the interval of convergence of the power series, we can use D'Alembert ratio test with modulus sign. Okay. Now we are remaining 2-3 series for testing whether it is convergent. exponential series, logarithmic series, and binomial series. So all are power series. So we can check it whether the series is convergent or divergent in the interval in which the value of x lies. Okay. So here exponential series. Exponential series. What? We know summation un equals to 1 plus x plus x square by 2 factorial plus x cube by 3 factorial. These are exponential series. So it is also an power series. So what is the interval of convergence of this series? That is the values of x. So this is very simple because see here un equals to what? X to the power n upon n factorial, and un plus 1 equals to what? X to the power n plus 1 upon n plus 1 factorial. Therefore un plus 1 upon un equals to what? Therefore limit n tending to infinity, this is equals to un plus 1 x to the power n plus 1 limit n tending to infinity x power n plus 1 upon n plus 1 factorial into n factorial upon x power n. So this is equals to what? X to the power n cancel 1 x n factorial n plus 1 taken outside, n plus 1 can be taken outside. So here we see that limit n tending to infinity what? 1 upon n plus 1 into x. Okay. So this is what? Its limit is what? 0 for all. Okay. Clear? And tending to infinity. This is tending to 0. So this is 0. 0 into x. X may be anything. So this is 0. Okay. And 0 is less than 1. Which is less than 1. For all x. For all x. That means converges for all values of x. Okay. So by ratio test, the exponential series is convergent for all x, for all values of x. You can also write for all values of x, for all values of x. Exponential series is convergent series. Okay. Now logarithmic series. Also for logarithmic series, what is the values of x for convergence of the logarithmic series? Just we have to find now. Take logarithmic series. Okay. Logarithmic series means x logarithmic series. X minus x square by 2 x cube by 3 minus 4 by 4 plus minus 1 to the power n minus 1 x power n upon n up to infinity. This is the logarithmic series. Logarithmic series. Okay. So here log 1 plus x, logarithmic series, that is what? Log 1 plus x. You can write also like this, log 1 plus x. Here un equals to what? Minus 1 to the power n minus 1 into x to the power n upon n. X to the power n upon n only. X to the power n upon n. Okay. So test for finding values of x for which this is convergent. Power series as a power series. So here un equals to this, un plus 1 equals to what? Un plus 1 equals to minus 1 to the power n plus 1 minus 1 and x to the power n plus 1 upon n plus 1. There, limit n tending to infinity un plus 1 upon un. Limit n tending to infinity un plus 1, this, minus 1 to the power n plus 1 minus 1 into x to the power n plus 1 upon n plus 1 into this in reverse order n upon minus 1 to the power n minus 1 into x to the power n. So it can be solved. Limit n tending to infinity x to the power n x to the power n cancel x n upon n plus 1 here minus 1 n upon n plus 1 into x. So this is equals to what? Minus x. Okay, this is equals to also minus x. So by ratio test, same thing here as exponential series, limit n tending to infinity un plus 1 upon un. So by ratio test, the logarithmic series is convergent if mod x is less than 1. Because we will take, because alternate series is this is alternating series. So we will take modulus sign, modulus x is less than 1, then convergent. Okay. And that is minus 1 is less than x less than 1. Now for minus 1 and plus 1, we have to check. For minus 1 and plus 1. For x equals to plus 1, we get series x equal to plus 1. For x equal to plus 1, we get the series what? 1 minus 1 by 2 square, not 2, 1 by 2 plus 1 by 3 minus 1 by 4 plus and so on. So this is what? Alternating convergence series. Okay, this is alternating convergence series. Because why? Alternately sign positive negative and each term is numerically less than the preceding term and 1 by n tending to 0. We get this, which is for x equal to 1, which is convergent by Leibniz test. And for n equals to minus 1, and for x equals to minus 1. For x equal to minus 1, we get what? Series minus 1 minus 1 by 2 minus 1 by 3 minus 1 by 4 minus and so on. That is what? Minus 1 plus 2 minus sum of 1 by n to the power 1, which is divergent series, which is divergent, So for divergent, as p equals to 1 in P series, where 1 upon n to the power p is divergent for p is less than or equal to 1. Okay, for by P series test, this is was n power 1 by n, summation 1 by n, 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, and so on. So this is by P series test, which is divergent. Okay. Thus, or hence, the logarithmic series is convergent for minus 1, divergent. So minus 1 is not taking in the interval. So this x is less than or equal to 1. That is, x belongs to minus 1 and 1. That is the interval conversing this. This is open here. Right. So minus 1 is less than, x is less than or equal to 1. This is the logarithmic series. Interval of convergence of the logarithmic series. Okay. Now finally, binomial series. Okay. Binomial series 1 plus x to the power n. Finally, binomial series. Binomial series 1 plus nx plus nn minus 1 by 2 factorial x square plus n minus 1 n minus 2 upon 3 factorial x cube plus n minus 1 n minus 2 up to n minus r plus 1 upon r minus what? N minus r. Here minus 1 2 factorial, minus 2 3 factorial. So here minus r minus 1, so r factorial, this plus infinity. Okay, this is the binomial series. Clear? 1 plus x to the power n. Here u r equals to rth term, just we are taking rth term because it involves n. So for counting we are using small r. So we can write ur equals to what? This is r 2 1 and this is for r equal to 0. So this is what? R plus 1 term. This is r plus 1 term. So this is r plus 1 term. So rth term. We are using r because here n is involved here. So rth term. What? n minus 1 up to this is which term? R plus 1th term. Before this, just we are getting here r minus 1, here r plus 2. So n minus r plus 2 upon r minus 1 factorial. This is rth term. And r plus 1th term. R plus 1 term is this. So n minus 1 up to n minus r plus 1 upon r factorial. Here r, we will use r. Then u r plus 1 upon ur. I think this is value. So what we can get here? Ur plus 1 equals to, because this is divided by this. So just write it n minus 1, n minus 2 up to this. N minus r plus 2, n minus r plus 1 upon this here in front side r minus 1. Before that r minus 2. So r factorial. This is ur plus 1 into in reverse order r minus 1 factorial upon this n minus 1 n minus 2 up to n minus r plus 2. Now up to this quantity will be cancelled out here. So we can write r minus 1 factorial. So r can be taken outside. R can be taken outside. This can be written as r factorial. R factorial equals to r minus 1 factorial. So r minus 1 factorial and r factorial cancel out. So r will be there. So here r and this n minus r plus 1. So this is the value. Now in place of nth term, so we are taking rth term. So we get limit r tending to infinity. Here r tending to infinity. U r plus 1. U r plus 1. U r plus 1 upon U r is this limit n tending to infinity, not n r. R tending to infinity. U r plus 1 upon U r equals to limit r tending to infinity. Here we see that just this upon this, r, so just divide by r here, n plus 1 upon r minus 1, we can get like this. Now r tending to infinity, this is tending to infinity, so this is 0 and minus 1, the limit is minus 1. Okay, so this is limit is minus of, here also x is involved here, na? Okay, this u r equals to x to the power r, x to the power r is also there. So here x to the power r, then x to the power into x to the power r minus 1. X to the power r is also there. X to the power r minus 1, x to the power r. So here x to the power r, x to the power r, and here x to the power r minus 1. So r cancel, x to the power minus 1 go to the upper side. So this is what? X to the x. This into x. Okay. So this into x equals to minus 6. We get this is equals to minus x for r greater than n plus 1. For r greater than n plus 1. Clear? Its limit is tending to 0, minus 1 into minus 6, minus 6. Here r is greater than n plus 1. R is greater than n plus 1. So this is my mod x. So by ratio test, hence by ratio test, the binomial series is convergent for mod x is less than 1. Mod x less than 1. This is for mod x less than 1. Convergent so binomial series is convergent for mod x less than 1, because we will take modulus sign, because this is the value. So here mod, so mod of x, that is mod of minus x, that is mod of x is less than 1. Then by ratio test, binomial series is convergent for mod x less than 1. So this is the completion of testing of series for convergence and divergence by using standard test, ratio test, comparison test, and in the case of alternating series we can use Leibniz test. The procedure for a series testing for testing of the series for convergence and divergence is what? First of all, see if the series having what? So first of all, which method we will use? What? If the given series is an alternating series, that is, terms are alternately positive and negative, then we can use Leibniz test. If series are positive term series other than power series, positive term series other than power series means not having x, power of x in the series, then we can use first find nth term and find the limit of un. If un tending to 0, then by Cauchy's fundamental test series will be convergent. And if tending to 0, then we can use comparison test. And if comparison test fail, then we can use further test, ratio test, reverse test, etc. Okay. So what is the process of our testing and power series? For power series, ratio test is used. If ratio test fail, then we can use any of the tests we have further discussed. Okay. So for testing a series, first of all see whether the series is alternating or not. If alternating series, not, we can use Leibniz test. If series is other than power series, that is not power x including in this series, then we can use for a series, find this limit. If not tending to 0, divergent. By use which method? Cauchy's fundamental test of divergent. If un tending to 0, then test comparison test and etc. And any of the test you can use. Okay, for power series, we can use ratio test. Okay. Now I will give some questions to you for solving. So write down one by one and do practice for determining the convergence and divergence of the series. Okay. So first question, discuss the convergence of the series. Discuss the convergence. Discuss the convergence of the series. Discuss the convergence of the following series. Discuss the convergence of the following series. First, one by one, just write. One by log 2 minus 1 by log 3 plus 1 by log 4 minus 1 by log 5, this. Second, (5 by 2 minus 7 by 4), 5 by 2 minus 7 by 4 plus 9 by 6 minus 11 by 8. 9 by 6 plus 11 by 8 minus 11 by 8. 5, 7, 9, 11, 5, 7, 9, 11, 2, 4, 6, 8, 2, 4, 6, 8, plus minus, plus minus, plus, and so on. And also series third, sum of n equals to 1 to infinity. 1 to infinity minus 1 to the power n minus 1 minus 1 to the power n minus 1 n upon 2n minus 1 n upon 2n minus 1 n upon 2n minus 1 minus 1 to the power n minus 1. Okay, so just try to solve for convergence or divergence. Okay. Here, this is minus 1 to the power n minus 1 minus 1 to the power n minus 1 1 upon 2n minus 1 1 upon 2n minus 1 1 upon 2n minus 1 and n log n square 4 sum of n equals to 1 to n equals to 2 to infinity 2 to infinity minus 1 power n log n square minus 1 power n log n square. Okay, and one by fifth 1 upon 1 minus x 1 upon 2 1 minus x square to 1 minus x square plus 1 upon 2 1 minus x square plus 1 upon 3 1 minus x square 1 minus x cube 1 minus x cube. This is power series. Okay, so 1 upon 1 minus x plus 1 upon 2 1 minus x square plus 1 upon 3 1 minus x cube plus to infinity. Six x upon root 3 x square upon root 5 x upon root 3 x square upon root 5 x cube upon root 7 x square upon root 5 plus x cube upon root 7 minus and so on. 7 1 So 3 questions or more there. Series 1 plus 1 upon n or minus n square. 1 plus 1 by n power minus n square. This is for root test. You can use root test here. Now 7 and then 8. Sum of n equals to 1 to infinity 1 upon log n power n. Log n power n. Log n power n. Log n power n. N equals to 1 to infinity. Okay. And then 9. Minus 1 n equals to 1 to infinity minus 1 to the power n x plus 1 power n minus 1 to the power n x plus 1 to the power n upon x plus 1 to the power n upon 2 to the power n n square. 2 to the power n n square. 2 to the power n n square. Okay. So just you have to solve up. Near about 10 questions. Okay. So here see that 10 1 minus 2 by 5 1 minus 2 by 5 plus 3 by 10 minus 4 by 7 1 minus 2 by 5 plus 3 by 10 minus 4 by 17 plus minus 1 to the power n minus 1 minus 1 to the power n minus 1 n by n square plus 1 n upon n square plus 1. The nth term is given here. Okay. 11. Question 11. One plus 1 by 2 square minus 1 by 3 square 2 square 3 square 4 square minus 1 by 4 square one plus 1 by 2 square minus 1 by 3 square minus 1 by 4 square and then plus 1 by 5 square plus 1 by 6 square minus 7 8, 1 by 7 square minus 1 by 8 square plus and so on up to infinity. Just you have to test for convergence, absolutely convergent for this. Okay. 1 plus plus minus minus plus plus minus minus and so on. Okay. One plus 1 factorial plus 1 upon 2 factorial plus 1 upon 3 factorial plus up to infinity. Okay. And 13, 1 plus 1 by 2 plus x to the power 1 upon 3, x to the power 2 upon 4, x to the power 3 upon 5, 1 by 2 plus x by 3 plus x square by 4 plus x cube by 5, 1 x square by 4 x cube by 5 plus and so on up to x to the power n upon n plus 2 to infinity. Okay. So these are the question, and also just write one more question. Sum of this is the series x by 1 plus x, x upon 1 plus x plus x square upon 1 minus x square, x square upon 1 minus x square plus x cube upon 1 plus x cube, x cube upon 1 minus x cube, 1 plus x square, 1 plus x cube, 1 plus x, 1 plus x square, 1 plus x cube, x square x cube, x square x cube, and so on. Okay. So this is and minus sign here. Minus sign. Okay. So x upon 1 plus x minus x square upon 1 plus x square, x cube upon 1 plus x cube minus and so on. X square x cube, x square x cube, plus minus plus minus, plus minus plus minus, 1 plus x, 1 plus x square, 1 plus x cube, and so on. Okay. So these are the questions. 14 questions you have to test for this. So alternating series. This is alternating series. Root test you can use here. Root test you can use here. Okay. Root test can be used here. And here also root test can be used. Alternating series is this. This is also alternating series. Alternating series as a power series or also simple series you can use here. So power series, just identify the value of x for which the series is a convergence. Just refer the books and solve these questions. Okay. So these are the discussion about testing of series, whether it is convergent or divergent. Okay.